we have to study about the motion of a charged particle in a uniform magnetic field. How a charged particle moves in a uniform magnetic field. We have learnt about this in the last class. We have learnt about this. This is Fleming's left-hand rule. So, in Fleming's left-hand rule, this thumb indicates the direction of force. This index finger indicates the direction of magnetic field, and central finger, this indicates the direction of current. So we have done it, and all these three parameters, force, magnetic field and current, they all are orthogonal to each other. Orthogonal means they all are perpendicular to each other. So keeping this in mind, let's start with this motion of a charged particle in a uniform magnetic field. When a charged particle small q moves in a magnetic field B vector, with a velocity v vector, then it experiences a force. So we know that when a charged particle moves in a magnetic field, with a velocity b vector, then it experiences a force F vector is equal to q into v vector cross b vector. Its magnitude F is equal to q v b, F is equal to qvb sine theta. Now, please come on to page number 26. Following three cases are possible. First case, when the initial velocity is perpendicular to the magnetic field. When the initial velocity is parallel to the magnetic field, means this v vector is parallel to magnetic field, then theta is equal to 0 degree. Whenever two vectors are parallel to each other, then angle between them is 0 degree and theta is equal to 0 degree. So in this case, F is equal to QVB sine 0 degree. Sine 0 degree is 0, so 0 into anything is 0. So in this case, the force experienced is 0. Now, second case, when the initial velocity is perpendicular to the magnetic field. Case second, when initial velocity is perpendicular to magnetic field, when v vector is perpendicular to magnetic field b vector. Here theta is equal to 90 degree. Here theta is equal to 90 degree. So F is equal to QVB sine 90 degree, and sine 90 degree is 1, so F is equal to QVB. Force is equal to QVB. All right, now F is equal to QVB. Now there is one diagram. A diagram is there. So let us try to understand it.
Yes.
So I'm going to draw this. It is very very interesting diagram. Let's just see. First of all, we will draw a circle here. Let's draw a circle here, and then This is the center of this circle, and consider that there is a small charge q. There is a small charge q. Q is here, and this q is going in this direction. Suppose that q is going in this direction, upward direction, and it is not moving in this circular direction. I will talk about this circle later on, but first of all, let us consider that this small charge q is moving in the upward direction. So what will happen, and what will happen, just see. uh, Anuja, this crosses means, I think I told you earlier also that crosses means it is into the page. It is inside the page. Okay. So these crosses means that the magnetic field is entering inside the page. So if we stretch our left hand's fingers like this, then this crosses means that magnetic field is into the page. So let us move our index finger like this. Index finger is into the page. Okay, now this charge, this q is positively charged. So positive charge, it is in this direction. The velocity of this positive charge is in this direction, v vector. Okay, so I told you that the direction, I told you the direction of positive charge. The direction of positive charge gives us the direction of current, and the direction in which negative charges flow, the current moves in opposite to that. The current moves in the opposite direction. If negative charge flows like this, then current will flow like this. Okay, so q is a positive charge. Positive charge is going in this direction. It means that direction of current is like this. So current is indicated by this one. Current is indicated by central finger. Okay, then central finger, move your central finger to the upward direction. So move your central finger to the upward direction, and this index finger, this is magnetic field. So magnetic field should be into the page. So central finger should be like this, and index finger should be into the page. Then thumb is indicating towards the left direction. Is this clear to you? Is this clear to you? Our hand is like this. We have to stretch our fingers like this. Magnetic field should be into the page. So we have to move it like this. Magnetic field should be into the page. But current, current is upward. So central finger, keep your central finger in the upward direction, and index finger into the page. Then thumb is indicating in this direction. So force will be in this direction. So it will experience this charge. Actually this charge is moving in the upward direction, but it is experiencing a force in this direction. It is experiencing a force in this direction. Again, it is going in this direction and experiencing a force in this direction. Again it will go in this direction, then experience a force like this. Again it will go in this direction, then experience a force like this. Again it will go in this direction, then experience a force like this. So the charge is going, the charge wants to go like this, but some force is pulling it inside. So it moves like this. The charge goes like this. Again someone pulls it like this. It goes like this. Charge wants to go in this direction, but Lorentz force is moving it like this. So like this, charge follows a circular path. Is this concept clear to you? Okay, then the same thing is written here. The direction of this force is perpendicular to both v vector and b vector. This force, the direction of this force, this is f vector. The direction of this force is perpendicular to both b vector and v vector. It is perpendicular to both. This force continuously deflects the particle sideways without changing its speed, and the particle will move along a circle perpendicular to the field. So this force continuously deflects the particle in the side direction, and so it moves in a circular direction. Thus the magnetic force provides the centripetal force. Let r be the radius of the circular path. This magnetic force provides the centripetal force. Okay, what is centripetal force? Centripetal force, a force which acts towards the center of a circle, is called centripetal force. A force which acts towards the center of the circle is called centripetal force. So this F vector provides the necessary centripetal force. The centripetal force is equal to centripetal force is equal to, Acha, what is centripetal force? Centripetal force is mv square upon r. So let us consider that the radius of the circular path is small r. So centripetal force is mv square upon r is equal to magnetic force. Magnetic force QVB. So mv square upon r is equal to QVB. Let's cancel this V by this V, and let us find out the radius of the circular path. So R will be mv upon QB. mv upon QB. Is this clear to you?
Yes.
Okay. Okay, let's move on to page number 27. On to page number 27. Now, period of revolution is equal to circumference upon speed. Okay, what is period of revolution? Period of revolution means that the time period which this charge takes to come to take one complete round. That is called time period. So, period of revolution or time period is the same thing. So, period of revolution is equal to circumference. Period of revolution is equal to circumference upon speed. Circumference upon speed. What is period of revolution? We say it capital T. Capital T. And what is circumference of this circular path? It is 2 pi r. And the speed is v. So T is equal to 2 pi r upon v. Now, is this clear to you? Circumference means the complete path, the complete distance covered by this charge. That is called 2 pi r. 2 pi r is the circumference. So circumference is the complete path which it follows in one complete round of this circular path. And speed is its speed. We have taken the speed of this charged particle as small v. So 2 pi r upon v, T is equal to 2 pi upon v into small r. So T is equal to 2 pi upon v. What is this small r? Small r is mv upon qb. mv upon qb. Let's cancel out v by this v. So T is equal to 2 pi m upon qb. T is equal to 2 pi m upon qb. The frequency of revolution is, okay, we know that the reciprocal of this time period gives us the frequency. So frequency of revolution is Fc is equal to 1 upon T. 1 upon t means reciprocal of time period. So qb upon 2 pi m. Is this clear till now?
Yes, sir.
Okay. Now we will go through case number third. Case first was that when v vector is parallel to b vector, when v vector is parallel to b vector, then magnetic force is zero. F is zero. Magnetic force is zero. When v vector is perpendicular to b vector, then when v vector is perpendicular to b vector, then in that case the charged particle want to go in a straight direction, but due to magnetic force deflects it sideways, and because of that magnetic force it follows a circular path. So the inward dragging force means centripetal force. So this centripetal force is due to what? Is due to magnetic force, because magnetic force is pulling it inside. So centripetal force is mv square upon r, and magnetic force is qvb. So mv square upon r is equal to qvb. V will cancel out this v. Mv upon r is equal to qb. Now r is equal to mv upon qb. All right. From here we have calculated period of revolution. Time period means time taken by a charged particle to complete one round of this circular path. So the total distance covered in a circular path is equal to the circumference of a circle. So this is circumference 2 pi r upon its speed. Speed is v, 2 pi r upon v. Now what is the value of r? Value of r is mv upon qb. From here we will cancel v by v. So t is equal to 2 pi m upon qb. This is called time period of revolution, and if we do the reciprocal of it, then it gives us cyclotron frequency. This is called cyclotron frequency. Actually, cyclotron is a magnetic device which is used in so many electronic equipments, but for the last 3 years it is not in our syllabus. But to calculate this cyclotron frequency, it comes in exam. Okay, so we have to do only this cyclotron frequency. Now we will do case number 3, when the initial velocity makes an arbitrary angle with the field direction. I am going to switch to the next slide. When the initial velocity makes an arbitrary angle with the field direction. Case number 3. And the initial velocity makes an arbitrary angle. Arbitrary angle means any angle other than 0 degree and 90 degree. Any acute angle other than 0 degree and 90 degree. When the initial velocity makes an arbitrary angle with the field direction. Arbitrary angle with the field direction. A uniform magnetic field B vector. Now we are on page number 27 in the central portion, page number 27. When the initial velocity makes an arbitrary angle with the field direction. First point, a uniform magnetic field B vector is set up along positive x-axis. A uniform magnetic field B vector is set up along positive x-axis. A particle of charge small q and mass m enters the field B vector with velocity v vector inclined at angle theta with the direction of the field B vector as shown. So let's draw three axes: x-axis, y-axis, and z-axis. Now, the direction of magnetic field. Now, this time we are considering that the direction of magnetic field is along x-axis. So we have marked B here. B is for magnetic field. The direction of magnetic field is along x-axis. Now, let us consider that this positive charge is making an angle theta with the direction of magnetic field. Velocity is in this direction and it is making angle theta. It is making angle theta with magnetic field B vector. Now, now when we have any type of, when we have any vector, velocity is also a vector. When we have any vector which makes an angle with the horizontal direction, then this vector gets converted. This vector gets split up into two components. One is horizontal component, another is vertical component. So what is horizontal component? Horizontal component is along the angle. So this is V parallel. We call it V parallel. And the component which is perpendicular to V parallel, this is V perpendicular. So we have named it by we have named it by V parallel and V perpendicular. Now, now the second point which is mentioned after this diagram, which I have not drawn, I am going to draw it. So the next point which has been mentioned on the last line of page number 27. The velocity V vector can be resolved into two rectangular components. Now page number 28. First, the component V parallel is equal to V cos theta. V parallel is equal to V cos theta. And second component V perpendicular is equal to V sin theta. Till now, is this clear to you? Is it clear till now? Anusha, are you listening?
Yes, sir, I'm hearing.
Okay. On page number 28 only, due to this component of velocity, the charged particle experiences a force F is equal to Q V perpendicular into B. So due to this component of velocity, the charged particle experiences a force F is equal to Q V perpendicular into B, which acts perpendicular to both V perpendicular and B vector. Anusha, we know that whenever the magnetic field and velocity, whenever the angle between them is 90 degree, then it follows a circular path. So now you see that this magnetic field is in this direction. This index finger is in x-axis direction. The magnetic field is in this direction, B vector. Magnetic field is in this direction. And this perpendicular component of velocity, and this is positive charge. The direction in which positive charge moves is the direction of current. So this is magnetic field. Magnetic field is in x-axis direction and current is in this perpendicular component is in upward direction. So it is in upward direction. Then where my thumb is going, my thumb is pointing into the page. It means that the vertical component is getting deflected inside. It is getting deflected inside. So it will form a circle like this. It will form a circle like this. But there is a parallel component also of velocity. There is a parallel component of velocity also. So circle is something like this, because circle is forming like this. So circle will be like this, but this parallel component of velocity is also pulling it in that direction. So this circle will get a little bit extended like this. It will form a helical path, because look, this magnetic field is in this direction and this V perpendicular is in upward direction. The magnetic field is in this direction and V perpendicular is in upward direction. So thumb is going into the page. So it will form a circle like this, only one circle. But this V parallel component, this horizontal component is also pulling that circle like this. It is pulling that circle like this. So it will form a helical path. A circle will get pulled like this. So I am going to draw the diagram of this helical path. The diagram of this helical path will be like this. Like this. One loop, second loop, third loop, fourth loop, and dot 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 like this, so on. Alright, is this clear to you?
Yes, sir.
Okay, now due to this component of velocity, the charged particle experiences a force F is equal to Q V perpendicular B, which acts perpendicular to both V perpendicular and B vector. This force makes the particle move along a circular path in the YZ plane. In the YZ plane, the radius of the circular path is the radius of the circular path the radius of the circular path is R is equal to mv perpendicular upon qb. What is R? R is mv upon qb. R is mv upon qb, and this time it is forming a circular path just because of this velocity. It is forming a helical path. This circular loops are getting extended in this direction because of V parallel because of horizontal component of velocity, but it is forming a radius, it is forming a circular path because of this velocity V perpendicular. So that's why I have written R is equal to mv perpendicular upon qp. Otherwise, if there was only this component V perpendicular, if there was only this component, then R would have been mv upon qb. R would have been mv upon qb. But here the components, there are two different components. So because of V perpendicular, I will write not mv upon qb, I will write mv perpendicular upon qb. Now what is V perpendicular? V perpendicular is V sine theta. So R is equal to mv sine theta upon qb. mv sine theta upon qb. The period of revolution is T is equal to 2 pi r upon v, circumference upon speed. Now this time we have to write V perpendicular. Okay, so T is equal to 2 pi upon V perpendicular into small r. T is equal to 2 pi upon, what is V perpendicular? V perpendicular is V sine theta. And what is R? R is mv sine theta upon qb. Upon qb. V sine theta will cut this V sine theta. So T is equal to 2 pi m upon qb. This is time period. Thus, a charged particle moving in a uniform magnetic field has two concurrent motion: linear motion along B vector and circular motion in a plane perpendicular to B vector. Hence, the resultant path of the charged particle will be a helix as shown. So, resultant path will be a helix as shown. Okay, now the linear distance. Now, the linear distance traveled by the charged particle in the direction of the magnetic field during its period of revolution is called pitch of the helical path. So between one loop and another loop, the distance between one loop and another loop, horizontal distance between one loop and another loop is called pitch. Pitch, P-I-T-C-H, pitch. Now pitch is what? Okay, consider that we are considering this path, that this loop is starting from this point and it is going up like this, like this, like this, like this, and then it is coming down like this at this point. So from here till here and here, it is going to complete one circular path. It is going to, because initial position and final position, they are at the same positions. So this has completed one circular path, and the horizontal distance covered by this helix is called its pitch. So how much time is taken to complete one circular path? How much time is taken? Time period is that time which is taken in completing one complete cycle. Is this clear to you, what I am telling you? Is this clear?
Yes, sir.
Okay, so pitch will be equal to, V parallel into T. Speed into time is equal to distance, horizontal distance covered. Speed into time. So what is V parallel? V parallel is V cos theta and what is T? T is 2 pi m upon QB. 2 pi m upon QB. So pitch is 2 pi m V cos theta, 2 pi m V cos theta upon QB. Okay, Anusha, clear till now?
Yes.
Okay. Now we will start with the next topic, motion of a charged particle, motion of a charge in perpendicular magnetic and electric fields. On to page number 29. We will start in 2 minutes. Give me 2 minutes break. Arusha, are you there?
Yes, sir.
Okay. Now, in page number 29, motion of a charge in perpendicular magnetic and electric fields. Now, we are going to consider the motion of a charge which is in perpendicular electric and magnetic fields. This topic is also known as velocity selector. Let's move on to the next slide. Velocity selector. Suppose a beam of charged particles, say electrons, possessing a range of speeds, passes through a slit S1 and then enters a region of in which crossed perpendicular electric and magnetic field exists. So suppose there is an electron beam and we have made a very small space for that electron beam to pass through a region. So let us consider that we have made a small opening. This small opening is called slit. This is electron, electron, So please draw a dotted circle like this. Consider that it is a circle. So here, what is this? This is a positive plate. This is a positive plate, and this is a negative plate. This one is a negative plate, and this one is a positive plate. Now, one electron is coming in, and we know that the direction of electric field is always from the positive terminal to the negative terminal. The direction of electric field is always from the positive terminal to the negative terminal. Like this. So this is the direction of electric field. This is electric field. Now let there be an electron which is moving with velocity v like this, which is moving with velocity v like this. Velocity v. And this circle which I drawn here, this is region of crossed fields. Region of crossed fields. Okay, so crossed fields means the fields which are perpendicular to each other. So electric field is from the positive terminal is to negative terminal. So electric field, direction of electric field is from the up to down direction, up to down direction. It is in downward direction. And what this crosses, which I have drawn, what this crosses indicate? This indicates the magnetic field, B vector. So B vector is into the page. So electric field is downwards, is in the downward direction, and magnetic field is into the page. Now this electron is coming from here, and we have made a very little opening here, and this little opening is called slit. So this is S1. S1 means slit 1, and this is S2. S2 means slit 2. So one electron is a negatively charged particle. So an electron which is not going through this direction, which is deflecting a little bit in the upward direction, it will be further more deflected towards this positive terminal, So some electrons will get deflected in this direction like this. So this direction we call it deflection by E vector. We call it deflection by E vector. Then after that, some electrons, because electrons motion are not in a straight line, electrons are randomly arranged and electrons move in random directions. So some electrons will go a little bit here in the downward direction. So some electrons are getting attracted in this direction. They move in this direction due to magnetic field. Why? Why due to magnetic field? Because if some due to magnetic field, they will get deflected like this. Why? Because this electron is going in this direction. This electron is going in this direction. It means direction of current. It means direction of current will be in opposite direction. So current will be in opposite direction. Yeah, it means that current is in this direction, and magnetic field is inside. So current is in this direction and magnetic field is inside. Then what is the direction of this thumb? Direction of thumb is downwards. That's why some electrons are getting deflected in the downward direction. So this is deflection by B vector, means deflection by magnetic field. Is that clear? Is that clear, Anusha? Anusha, are you listening?
Yes, sir.
Okay. So some electrons are getting deflected towards the positive terminal, so they are getting deflected in the upward direction. Some electrons deflects in the downward direction. But there are some electrons on which the electric force and magnetic force are equal and opposite. So that electrons pass on undeflected and they go straight and they come out through this second slit, means a second opening. They come out through this second slit, and these electrons are called undeflected electron. undeflected electron. Undeflected electron. Now, the magnetic field B vector acts normally into the plane of paper and deflects the electron in the downward direction. Magnetic field deflects the electron in the downward direction. Next, only those electrons will pass undeflected through the slit S2, this second slit S2, on which the electric and magnetic forces are equal and opposite. The velocity of the undeflected electrons is given by velocity of the undeflected electron only on those electrons on which electric force is equal to magnetic force. Electric force is QE, and what is Q here? It is an electron. It is an electron. So charge on an electron is small e. So small e into E, and magnetic force is whenever velocity, whenever the direction of charged particles and the magnetic field, whenever they are perpendicular to each other, then magnetic force is QVB. And what is Q here? Q is small e. So EVB. E will get cancelled out by small e. V is equal to E upon B. V is equal to E upon B. Such an arrangement can be used to select charged particles of a particular velocity out of a beam in which the particles are moving with different speeds. This arrangement is called velocity selector or velocity filter. Anusha, is this clear till now?
Yes, sir.
Okay. So, to So we are going to do till here only today, and next we will continue in the next class. Okay.
Yes, sir.
Okay, Anusha.
Thank you so much. Have a good day.
Okay.